Thank you, Darkan. So actually, for now, something completely different, as you're going to see. I'm a professor in particle physics at the Swiss Institute of Federal Institute of Technology. And well, I'm doing research in particle physics at Cern. So I will tell you a bit about Cern, and actually I will try to give you a few insights into the inner workings of nature. And I will give you a few thoughts to think about over the weekend, or maybe longer, we will see. Let me start with a very general observation. It is quite remarkable that modern science, or we in basic research, we are able to describe and study phenomena which occur on an incredible spectrum of, for example, length scales, distance scales. From the shortest distance scales which ever appeared in our universe at the very beginning of the universe, up to the biggest things in the universe, up to the size of the universe itself. Now, in our daily life, we are just used to a small part of the spectrum. We are used to distances like inches or miles, feet. Well, I come from Europe. I would rather say meters or centimeters. These are the distances we can see with our eyes. So we can think about it, we understand them, and so on. So it seems then if we put these kind of distances we are used to think about onto such a ruler as I have here, it turns out that apparently we, or at least some of us, are sitting right at the center of the universe. Now, if we, well, I think you knew that already, so I didn't have to tell you. Now, if we go to very big things, like you want to study galaxies or how galaxies move in our universe, you know that the eye is not a good tool to study this. So you need other tools. And the tools which you need to study the big things are the telescopes. On the other hand, if you want to study small things, again, you need special tools. Probably from school, you know that, maybe you probably used it there, to look at very small things like a cell, like a human cell, you use an optical microscope, and you see these tiny things. However, it turns out if you want to look at things which are much smaller, for example, than a cell, then an optical microscope will not do the job. Even if you buy the best one in the world, it will not work. For example, if you want to look at an atom is so much smaller that an optical microscope will never allow you to see it. So you need special microscopes. You need different types of microscopes. And in fact, what you can take as a take-home message is, whenever you hear about these gigantic accelerators, these super particle smashers, and I will talk about these more in the following, then you just have to think about them as super gigantic microscopes. And with these microscopes, over the last 50 or 100 years, we could look into the structure of matter in a finer and finer way. And we can now see things which are even much smaller than atoms. Now, how small? Let's have a look at this one, at the basic building blocks of matter. You all, again, know from school, I'm sure, matter is made out of molecules. Molecules are made out of atoms. And atoms, I'm also sure you know this, have the structure that at the center of an atom, you have the nucleus, where almost all the mass of the atom sits. And then around the nucleus, you have the electrons just going around the nucleus. Now, how big is an atom? The diameter of an atom is typically 1/10 of a billionth of a meter. Now, that is small. That is a millionth of the thickness of a human hair. So that is small. But for a particle physicist like me, that is huge. It's gigantic. And we are looking at things which are way, way, way smaller. Now, here comes an important observation. This was the size of the atom, of the whole atom. Okay? Now, what is the size of the nucleus? Turns out that the size of the nucleus is 1/millionth of a billionth of a meter. That means the nucleus is about 100,000 times smaller than the whole atom. That means all these drawings of the atoms which you have ever seen in the books and wherever you've seen that, they are all wrong. They're all wrong because in principle, if you put it to scale, if you draw an atom to scale, you would not see the nucleus because it's so small. It would be a point. basically, on such a drawing. Okay? Now, knowing this, there comes another observation. So we see there is the nucleus, and around are going around the electrons, and everything else is nothing. There's just empty space. Okay? And now comes my first thought for you. If you compute the volume of the atom and you compute the volume of the nucleus, you find out that more than 99.9% of the atom is empty space. Now, we are made out of molecules. We are made out of atoms. So this means we are made out of more than 99.9% of empty space. Everything, everything. Now, I think that is the first interesting thought for the weekend. Now, some of you might say, what is this guy up there telling us? He must be completely nuts. I mean, why can't I pass my hand across this chair if all it's empty space? It should be possible, right? Why am I not starting to fall across the floor right towards the center of the Earth? And here comes an important observation again. It shows us that it is not enough just to know what the building blocks of matter are. It is very important also to understand what the forces, what are the interactions between the building blocks. Because, after all, it is the forces in nature which make the world appear as it appears. It is the forces between the atoms at the upper layer of my hand and the upper atoms on this chair, which at some stage become so repelling that I cannot pass it through. It's not because matter is continuous, it's just the forces. It is the forces between, for example, light and the atoms in the wall which avoid that the light goes through. It's not because the wall is continuous. Actually, it's all empty. But because of the interaction of the light with the few particles which are there in the wall, the light cannot pass through. So that is the first important thing to remember. So then, this was the atom. The structure of the atom was discovered about 100 years ago, and then around the 1930s, it was found that actually the nucleus is made out of smaller particles. There are these protons. The protons are positively charged particles, and the neutrons. Okay, I will come back to the protons at the very end of the talk, so remember protons. And then, in the 60s, in a very beautiful experiment, actually not far from here, in SLAC, it's near Stanford, it was discovered that inside the protons and neutrons, there are even smaller particles, the so-called quarks. So these are the three particles over there. Let me use a better pointer, which I brought directly from Switzerland. So this wouldn't pass through security, I'm afraid. So there are the quarks inside the protons and the neutrons. And these quarks, there are three, these quarks, together with the electrons, are the most fundamental particles we know of today. They are so small that even with our best microscopes, even with our best accelerators, we cannot see any substructure of them. Doesn't mean that they don't have it. We just can't see any substructure. And here comes the second interesting observation. Now, again, from daily life, you would be used to the following thing. If you have a box full of apples, you would expect that the weight of this box is just the sum of the weights of all the apples plus the weight of the box. Okay? Now, if the same thing applies to, let's say, our weight, then our weight should be nothing else than the sum of the weights of all the quarks and the electrons we are made of. After all, we are just made of these particles. And now if you do this and you measure it precisely, it turns out that with this method, you only get 10% of our weight. That is as if the total weight of the box would be 10 times bigger than the sum of the weights of the apple and the box. So where is all the weight coming from? Where is this 90% of the weight coming from? And it turns out that 90% of the whole weight comes from pure energy, which is related to the force which binds the quarks together very tightly. Because Einstein told us that energy is equivalent to mass, or weight. That means whenever, every day in the morning, you step on your scale and you measure a weight, I don't know what it is, 150 pounds, whatever, basically, you are measuring the weight of pure energy. I think that's also an amazing thought. at least for me. Pure energy, mostly pure energy. Now, studying these smallest things of nature at the same time helps you to understand also what's going on at the big scales in the universe. There's a tight connection. And this connection I can show in the next slide. Now, in a very short time, I show you the whole history of our universe. Here it is. All experimental evidence points to the hypothesis that our universe was born in a Big Bang, in a gigantic energy explosion about 13 billion years ago. And in the beginning, you must imagine the universe as a gigantic soup of particles. Well, first it was small, and then it became bigger and bigger, and gigantic soup of particles, which just expanded and cooled down. And the important thing is that this soup was opaque. It means it was not transparent to light. So during about the first 300,000 years of the universe was not transparent as it is today. Light could not propagate. Okay? Only after about 300,000 years, after the Big Bang, the first neutral atoms formed, and suddenly the universe became transparent. And since then, light can propagate across the universe. And then the first stars formed. After some hundreds of millions of years, then the first galaxies formed. Certain stars died again in explosions. New stars were formed, and so on and so on. And some 4 billion years ago, our star was formed. And then the Earth was there, and we are there. And our colleagues, the astronomer and astrophysicists, for example, with their telescopes, they are now looking back into the history of the universe. Why looking back? Whenever you look at an object which is far away, you see the object as it was some time ago. Because light takes some time to go from the object to your eye or telescope. So whenever, for example, we look at our sun, we see the sun as it was 8 minutes ago. You will never be able to see the sun as it is right now. So if somebody is going to steal our sun, we will only know it 8 minutes later. So these guys will have 8 minutes advantage to run away. Now, if the astronomers look at, for example, galaxies, at a galaxy which is 5 billion light years away, then it means we see this galaxy as it was 5 billion years ago. We don't see it as it is now. We see it as it was 5 billion years ago. Maybe by now it doesn't even exist any longer. And so the astronomers have nothing else to do, just look at objects which are further and further away, so they look more and more back into the history of the universe. The problem is they cannot look back right to the beginning of the universe, right to the Big Bang. Why? Because the universe was not always transparent. They can only look back up to the first 300,000 years, up to this moment when the universe became transparent. No way to go further. So how can we study the universe during this first phase? And here we particle physicists come in again, because what you can do is you can try to recreate in the laboratory, again with our particle accelerators, conditions of matter as they existed short instances of time after the Big Bang. And I'm talking even fractions of a second after the Big Bang. And if we understand what is going on between these particles and what are the forces and so on, then we understand what has happened in this early phase, and then we understand better why the universe has developed as it has developed and how it might develop further on. Now, it seems that many things are understood, but actually there are a number of big open questions. Now, the first one I alluded to already, we are still trying to understand in all detail what was really the behavior of matter and which particles were there, let's say fractions of a millionth of a second after the Big Bang. Another question is, you might have heard it, 2 years ago, a very important discovery was made at Cern in Geneva. We found a new particle of nature which was never seen before. It was dubbed the God particle in the newspapers, although it has nothing to do with God, at least as much as I know. And it is a very important particle. It was predicted 50 years ago, because it explains us why all the other particles, like these quarks and electrons, why do they have mass? Now, we have found this new particle. We are now studying it. But of course, the question is, are there other particles out there in the universe which you have never seen before, and which might help us understand better our universe? And in fact, our universe has a big puzzle for us. If we look out in the universe, we see that there is a lot of so-called dark matter. Matter which is not shining as all the stars are doing. That's why it's called dark. But we see the influence of this matter on the motion of the galaxy. So we know that it must be there because the galaxies move in a certain way, and it can only be explained by additional matter which is out there, which is not shining. But we don't have a clue out of which particles this matter is made of. So we are kind of in the dark there. That might be another reason why it's called dark matter. And there are certain theories which make proposals for new particles which we might discover in our accelerators. Now, these are really big science questions. And for answering big science questions, it turns out you also need big scientific infrastructure. Infrastructure like accelerators, which you cannot have in your lab at the university. Not everybody cannot have it because it's just too complicated, too expensive. So you need special laboratories around the world. There are only a few ones. And one of them, and actually by now it's the biggest laboratory of particle physics in the world, is Cern. Cern is the European Laboratory for Particle Physics, although by now it's becoming the global, not only the European, but the global laboratory for particle physics. What is its mission? Well, first of all, and that is not a surprise, we want to push the frontiers of knowledge. I explained a bit what these frontiers are. However, it turns out that when you want to do that, when you want to design experiments, very often it turns out that for building our experiments, we would need technologies which are not there yet. We cannot buy them. So what do physicists do when they cannot buy something? Well, we build it ourselves, or we invent it ourselves, typically, if we manage. Or we go to high-tech companies and we try to invent it together with the high-tech companies. And this has occurred again and again and again. The interesting thing is that often certain technologies, or these technologies which are developed for our experiments, then make it to our daily life. Sometimes very quickly, sometimes over longer time scales. I will come back to that at the very end of my presentation. Now, a very, very important other part of the mission of Cern, this was said also earlier on today, is we have to continue to train the scientists and the engineers of tomorrow. If we don't do that, then we are doomed. I mean, these are the guys which will make the world a better world, definitely in the future, but we have to train them today. And finally, at Cern, something very interesting happens. By doing all this, as it is described here, we bring together people from all over the world, across all types of political boundaries, religious, ideological, whatever, you name it. And they all work for the same goal. And we're talking about tens of thousands of people, the best young scientists all over the world. Why does it work at Cern? And why is it so difficult often in the normal life? At Cern, we have the advantage that we can formulate one goal, which is basically the same for everybody. The goal is, let's try to understand nature better. Now, in normal life, it's almost impossible to define one goal which is the same for everybody, right? But here it works, and it's really fascinating then to work together every day with people from all over the world. Now here you see the region around Geneva. Maybe you can see here the Lake Geneva, the airport of Geneva. Here is the Cern site. And what is indicated here is the circumference of a tunnel, which is 100 meters underground. And in this tunnel, we have installed the most powerful accelerators of all times, the so-called Large Hadron Collider. Now, the circumference here is about 16 miles, 27 kilometers. And in this accelerator, we have particles going around at almost the speed of light. That means these particles, they make about 11,000 turns a second. 11,000 turns, 16 miles. That gives a little bit a feeling for the speed of light. It's fast, but it's not super fast. I mean, whenever I drive my car from here to my experiment, I get this feeling for the speed of light because it takes me half an hour and the particles, it takes a bit less. Now, there are particles going in one direction, the others in the other direction, and there are 4 points where we make the particles collide. And around these 4 points, we have installed gigantic detectors, which are nothing else than big digital cameras somehow, which take a snapshot of every collision of particles. Okay, that's the idea. Now, to illustrate that a bit better, I have this video here. So this is a view inside the tunnel. You see the accelerator. And you will see that the scientists, we write the equations on the wall so that we don't forget them. And then the particles pass also the French-Swiss border 20,000 times a second. No immigration formalities there. And here you see the quarks inside the proton. And we have protons, actually many of them, going in one direction, the others coming from the other direction. And again, we use Einstein's equation that we can transform energy of these particles into mass of new particles. So in this collision, new particles are created, and they move away from the interaction in all directions. And the goal is to take a snapshot, make a picture of this interaction. So for that, we have to build this gigantic camera around the collision point. Now, in the next slide, you will see that why I say gigantic, because these are really big. These are definitely not portable cameras. To give you an impression, this is a picture of one element of our detector, about 1,000 metric tons, lowered 100 meters through this pit here. Or here's another picture. This was the heaviest element of our detector, which has the weight of about 5 jumbo jets. Okay? And we lowered them these 100 meters, and we were very careful because we only had one piece of each. And everything worked out very nicely, although it was one of the most exciting days. I was pretty nervous, but it worked out fine. And here are a few pictures. You see people working on the most central part of the detectors. Inside here, the particles are colliding. I don't know if you can see the people, but it gives you maybe a bit of a feeling for the size of the detector. This, for example, is about 12,000 metric tons heavy, 50 meters in diameter, more than 20 meters in length. Here another picture. Here you see the beam pipe where the particles are moving, and these are the elements of this gigantic camera. And then we closed it, and we were ready for taking pictures, basically, of collisions. And since 2009, we have been taking these collisions, and we have been taking pictures, many hundreds of billions of these pictures, many of these collisions. And we were looking for a few pictures which would indicate to us that the new particle was created. Out of these many pictures, which all are just known particles, we were looking for pictures which had, let's say, features which could give us evidence that new particles were created in these collisions. And I told you we had many, many billions of these images, which were, of course, analyzed via special algorithms programmed by our PhD students and so on. And after all, you have to imagine this is more than the classical search for the needle in the haystack. Because one problem is that we get the haystack 40 million times a second. Because we have 40 million times a second a collision. So that's pretty bad if you get so many haystacks. You're working on one and then the next comes. The second problem is our needle, for example, the Higgs particle, the needle basically looks like a piece of hay. So that makes the problem also worse, right? But we managed. We managed to go across these haystacks, and we managed to find images, pictures, which then gave us evidence that we had produced and discovered a new particle. And it was recognized that this was pretty important. Here, for example, the Science magazine, which in 2012 called it the breakthrough of the year. But there were also journals which you might maybe read a bit more often than the Science magazine, I don't know. For example, The Economist. Even The Economist called it a giant leap for science. And then even the colleagues in Stockholm, in Sweden, thought that this was pretty important. And they awarded the Nobel Prize in Physics last year to these two gentlemen, these two theorists, which actually had invented or predicted this particle 50 years ago on purely theoretical grounds, purely theoretical thinking. And now, 50 years later, we discovered it, that it really exists in nature. Now, here is the equation for all this. Is maybe for later discussions. Doug can have a look at the equation, because I'm going to examine you then. Now, all this means a lot of data. And now maybe you see a link to this event. Every detector has about 100 million readout channels. So it's like a 100 million pixel camera. That doesn't sound so much, but again, we are taking 40 million pictures a second. That you cannot do with a digital camera unless you're pretty nervous. And we have, if we take the data of all experiments together, we get about 3 gigabytes per second. Or we get 25 petabytes a year. Now, 25 petabytes, I know, to you doesn't sound so impressive any longer. However, you have to realize the following. 15 years ago, when we designed the experiments, we knew that we will have to handle 25 petabytes a year. And 15 years ago, 25 petabytes was a huge amount of data. And we did not have the technology to handle it. So Cern developed a technology which then was foreseen to handle, in fact, this data. So Cern developed, for example, so-called grid computing. The basic idea being that the data are produced at Cern in our collider, but then we distribute these data very quickly to about 140 computer centers in 40 countries. Instead of keeping them just at the computer center at Cern, we distribute them all over the world. It also avoids that several thousand scientists would like to access the computer center at Cern. That would be impossible, right? And now the scientists, the thousands of scientists, can access this data all over the world. That was the grid computing. The structure of this system is also a tiered structure. There's a tier 0, but basically Cern, where the data are produced. Then they are distributed to a small number of big computer centers. They are called the tier 1 centers. And then there are many more smaller computer centers, again, all around the world. And then the scientists basically access the data at these smaller centers. And there's a big data transfer up to 7 gigabytes per second from the data from the experiments to tape or disk. And the scientists use this system. Here is an example. An important number is we had, for example, 40 million jobs per month submitted to this system. So these are the analysis jobs which the PhD students submit. They run over a set of data and bring back a certain statistics analysis, for example. And 40 million jobs a month is quite a lot. However, there are many, many more data to come in next years because the accelerator now has been running for 3 years and it will run for much longer. So roughly, we have only collected about 1% of all data. That means Cern, of course, is forced to follow technology developments. And this brings me to a nice example of a successful public-private partnership. At Cern, we have OpenLab. What is OpenLab? It's a very special public-private partnership with the following idea. The motto is written here. The idea is you make it and we break it. That's the idea. I will come back. I will describe in a second what it means. We are talking about domains like automation control. Of course, domains like data storage and the cloud is being looked at, of course, data analytics, security, and so on. Now, what is the idea behind it? The Cern requirements definitely push the limit. Cern has very, very tough requirements on IT technology. And then, via this partnership, Cern gets access to early developments, new developments in leading IT companies. You have seen some of them on the previous slide. And then together with the IT companies, there are very rapid development cycles. So the companies get access to the IT infrastructure to test the developments. And Cern tests these developments. And so via these rapid cycles, the products get better and better. And in the end, you have a very classical win-win situation. We scientists get what we want or what we need, and the IT companies get a toughly tested product which then can be sold to the market. And this has been working now for about 10 years and has been pretty successful. Now, probably some of you ask, after all, so what's for? I mean, why do we spend so much money for these accelerators? Crazy things. Now, one answer is the following. I think you heard an important answer already this morning from Mrs. Napolitano. I mean, she made a big plea for the importance of basic research. One answer is that what we're doing is a cultural activity. You might be surprised, but I see myself as somebody who does cultural activity. Why? Because basic research is about knowledge. It's about increasing knowledge. And knowledge is a fundamental pillar of human culture. If we cut off that pillar, then we cut off a lot of our culture. And of course, we cut also off later developments, because all applied science builds on basic science, it builds on the fundamentals of basic science. Besides that, this general consideration, there are other, let's say, reasons why to do it. Because it turns out that there are sometimes very interesting spin-offs, like the World Wide Web. We heard about HTTP this morning, but I have to say, the World Wide Web, the idea of the hyperlink, was invented at Cern by Tim Berners-Lee. I'm sure you know it. The idea was, basically, he wanted to develop a system which would ease the work of the engineers and the scientists, which in the early 80s or so were designing this new accelerator. And he wanted to ease the work for exchanging documents and so on. So he invented this hyperlinking system. And then he showed it to his boss. His boss said, interesting, but vague. Well, it's not vague any longer. You know that it has revolutionized, basically, our world. Cern did not put a patent on it. If Cern would have done that, we could probably build an accelerator every week or so with the money. But on the other hand, I think it was good that this did not happen, because otherwise, since it was open, it helped the web explode as it exploded. Now, there are other examples of spin-offs, especially in the area of medical applications. Particle physicists, we are experts on accelerators, we are experts on detectors, and somehow also experts on IT technologies. And we can try to bring that to the medical field. For example, particle accelerators or beams from particle accelerators can be used to treat very effectively cancer. Actually, it turns out with this kind of accelerators and beams on accelerators, you can treat cancer in a much more effective and precise way than with the more standard traditional radiation therapy. The problem is, of course, it needs a lot of big, expensive infrastructure, so you cannot have it in every hospital. My vision for the future is that the accelerator developments, technologies will improve such that the accelerators become more and more compact, and then maybe sometimes in the future, many, many more hospitals can have such an installation, and so many, many more patients will get access to this modern technology of fighting cancer. Another important area is making images, medical imaging, biomedical imaging. Think about it. If you go to the doctor and you have an X-ray taken, basically you're doing a particle physics experiment. Because X-rays are nothing else than particles which cross your body and end up on a detector. The detector so far was always the film, right? But now these detectors are more and more replaced by electronics devices. And the whole technology for these kind of electronic devices comes from the field of, for example, particle physics. Also, other imaging devices, like, for example, positron emission tomography, also to study cancer and so on, they were developed, after all, from particle physicists, together with people from the medical sciences. For example, even myself with my own group, we are currently working on the development of a completely new device, imaging device, for preclinical studies. And basically all the know-how and the technology for building this device, a small device, is coming from the know-how which we acquired by building this huge experiment I showed you before. And finally, this grid technology of distributing the data can also be applied, for example, to the medical sector. I think there is one project in Europe where the idea is to distribute, for example, data from systematic scanning, like mammography scanning, to many hospitals all over Europe. Because if a doctor gets access to many more data than just the data of his or her own hospital, then he can get better statistics, better diagnosis, okay? And this is trying to be implemented. So far about some examples of spin-offs. Now there is one more thing, or actually I have three more things, or three more thoughts for you. The first one is the following. Look at your finger, or think about your finger. In your little finger, or in this finger, or every finger, there are more atoms than there are stars in the entire universe. And there are many stars in the entire universe, about 10 to the 22. So 1 and 22 zeros, a big number. In your finger, there are more atoms than 10 to the 22. And isn't this amazing? It tells us how an amazing structure we are made of. It's absolutely mind-blowing, at least for me. This is the first thought. Second thought. I told you about the protons, which are making part of the nucleus. Actually, it turns out that almost all the protons which exist in the universe, that means also all the protons which we are made of, they were produced 3 minutes after the Big Bang. And then they were there, and they didn't disappear any longer. That means we are made of material which is 30 billion years old. So all our building blocks were made basically 3 minutes after the Big Bang. Isn't that amazing? 13 billion years old, for that we look pretty good still, right? But think about it, think about it. It's fantastic. Finally, these are the protons, so these are the building blocks of the nucleus, which are so old. However, of course, we are also made of heavy elements. For example, you all have iron in your blood. Okay, there are iron atoms in your blood. Where does the iron come from? Actually, iron is not made in the first minutes after the Big Bang. Iron is only made in stars which die, which explode. Because then inside the star it gets so hot that you can have fusion of lighter elements up to heavy elements like iron. And then this iron is produced in these exploding stars, and the elements are thrown out into outer space. And later on it can gather again, and then maybe a new star is formed, and the planets are formed. And somewhere here, I mean in this place of our universe, there must have been stars exploding more than 4 or 5 billion years ago, where some of your iron atoms were formed. They were thrown out into outer space. They ended up one day on Earth, and one day they ended up in your body. That means it is a scientific fact that we are made of stardust. Thank you very much, and have a nice evening.